Welcome to a lesson with Dr. Val. Let's take a look at the idea of projection length. And specifically, our goal with this little video is to um, come up with a formula for how long a vector is, for the length of a vector, but doing it while thinking about projection length. Now, there was a video previous in this series that shows that projection length onto a unit vector, a vector of length 1, actually is a linear transformation. So if the vectors are in Rn, this linear transformation is from Rn to R, and it's actually given by the unit vector itself thought of as a row. So if V and U are column vectors, we could think of this row as U transpose, or UT, which makes the column into a row. So this is like a row now. So we can think a row times a column, UTV. So we're inputting V, and we're going to output what V's projection length is on U. So here's V, here's a unit vector, U, and the projection on the length in the projection length in the line that U defines right here. Okay. So that's what we're looking at right now. Now, it could be positive or negative. Negative, if V is pointing in the opposite direction of U, then the projection would be a negative. Okay. So we have this nice linear transformation. We can put V into it, and it outputs a projection length. All right. Now, another way of thinking about what UTV is as a dot product. U dot V. Here's a little example. Let's suppose that we have 1, 3. Now, this is not a unit vector, but this is just going to illustrate the idea of dot product. So if we have 1, 3, right, as a row vector, and we have a column vector right here for 2, and we matrix multiply them together, it's the same thing as going 1 times 4 plus 3 times 2. So if we line the vectors up this way, both as rows, 1, 3, 4, 2, multiply this column, multiply that column, then add the results. 4 plus 6, we get 10 in both cases. So this is a common notion between vectors, whether or not we think of them as rows or columns. Yet UTV in this particular case is the dot product. Okay, row times column. All right. Now, suppose that U is not a unit vector. How does this change? Well, you just make it into a unit vector. You divide out by the length of U. And we're going to talk about what the length of U is based upon this idea. But basically, what does that mean? Well, you think of 1 over the length of U. So notice we're using absolute value signs right here to represent length, or magnitude away from 0 if you like how far something is from 0. So we'll think of it that way. So this is a scalar right here, and we're simply multiplying it to the vector U, and it'll change it to be a unit vector. So U currently has a certain length, but if we rescale it down by dividing by that length, we get down to a unit vector. Okay, so we can always, so if we want to represent V onto the projected onto the line that U defines, we simply need to change U to be a unit vector, and then this would work right here. Or we could notate it this way with a dot product symbol right here. Maybe make it more bolder to represent it's a dot product between vectors, not matrices in this case, but a dot product. And so you have a unit vector dotted with V. So that's projection length of V onto the line described by the unit vector. Okay, so now let's think about length of a vector, suppose W. So the length of a vector W is equal to the projection length of W onto itself. So if you project W onto itself, onto the same line that W is on, that should be the length, right? So let's think about that right now. So even if we didn't know how to compute length, we still have this idea. length is equal to W divided by its length, dotted with W. Okay, so then what can we do? Well, we multiply both sides by the absolute value of the length of W right here. So the length of W squared is equal to the dot product of W and W, square root, and there we are, right here. Okay, and it will be, since we're looking for length, I mean, this is going to be a positive value. Now think about what W dot W is. So W, so it's the same thing as like row, W thought it was a row, times W thought it was a column. So if there were 4 entries, W1, W2, W3, W4, and then you had like W1, W2, W3, W4, think of what would happen. This times that times that times that times that, or you just dot product across first entries multiplied, second entries, third entries, fourth entries. It's just the sum of squares. It's a square root. It's a generalization to the Pythagorean theorem to more dimensions than just 2. But that's how we find the length, and it comes from these few ideas that we had here. That projection length is a linear transformation that kind of drives us into being able to use a dot product, and then using this setup right here, we can rearrange and solve, and we get that. Thanks for watching.